wallets, all you guys, you don't have a future. So all the devices will come with ARM, Enclave, what they already have, right? They already have them, but they're going to improve them and put the firmware and the 8.4, these crypto keys. What does that mean? Because that means that you'll sign inside the Enclave. Your keys won't need to be exposed. You as a dumb user, don't worry about it, because now when you want to do a transaction, it'll prompt you, oh, authenticate me, Face ID, fine. Enclave signs, crypto transaction, away you go. That's how you get to Walmart. That's how you get 6 billion people doing crypto. You ain't going to do it with MetaMask. Okay? You ain't going to do it with them cutting and pasting address keys and worrying about public keys, private keys. Where's my key? Oh my God, what's my passphrase? Where is it? Okay? That's where we're headed. So learning Solidity is good, right? Because it is the future, right? But understand, I'll say right now as we get started, so that you understand the context, the dApps are over here, the smart contracts are over here. They're not coupled, only logically, because today they're created by the same person. But tomorrow, they probably won't be, because tomorrow it'll be an API-driven smart contract world. Okay? So I have the best smart contract out there. I have IP that's patented, licensed, approved. I spent $1 million making this baby hum and get approved by regulators. So you do want to use it. Oh, by the way, if you are X, you must use something like this because it's regulated and mandated. And I'm the first one, whatever. So you get it. It's going to happen. Okay? So contracts. Boom. APIs. Think of Twilio. Made $1 billion business doing nothing but APIs when everybody else was doing web apps. How can you build $1 billion business just publishing APIs, Twilio? Well, let me show you. Now we have an API economy. Right? So the whole ecosystem we have called web apps is breaking apart and decentralizing into what's microservices, nanoservices, APIs. Johnny, the 12-year-old genius, has an API. Everybody wants it. He put it up for school. He's a millionaire. It's like a gumball machine. Boom. And it's all with crypto. Okay. So the contracts and then the dApps. So remember, so the dApps are what obviously will be the front end that will then use those APIs. So at the end of the day, the dApps matter. Right? They matter. But they're both important, but they're both separate. So understand the separation of concerns there. With that, take it away. Solidity from ground up.
Solidity from the ground up. Hi, my name is Dylan Beckwith, and I'm going to be talking about Solidity today. So before we get into what Solidity is, we're going to have to talk about transactions on the Ethereum blockchain. It's important to know that there are two types of account. There are externally owned accounts, EOAs. That is what an account is, owned by someone. And this has a private key. This is what people will sign up for when they sign up an Ethereum account. And then there are contract accounts, which contain a balance, just like externally owned accounts, but they also have a storage, which stores the code. So a transaction is a message that is sent from one account to another. So if an EOA is sending it to another EOA, then it's just sending balance information, like depositing money to another account. And contract accounts can send also transactions to each other, and they can include binary data, which is the payload, and they can include ether. If the target account contains code, that code is executed and the payload is provided as input data. So that's for like a contract account. It's going to receive the data, the binary payload, and then it's going to execute its code. Transactions are either not done at all or completely applied. That's the basis of the blockchain. That's very important to remember. And transactions per block is based on the gas limit. So you can only have a certain amount of transactions per block. If it's a very expensive transaction, there may only be one transaction per block. So gas, that is the cost of running code. Some people say Ethereum is to gas as Bitcoin is to gold. The Ethereum protocol charges a fee per computational step that is executed in a contract or transaction to prevent deliberate attacks and abuse on the Ethereum network. So gas is this execution fee that senders of transactions need to pay for every operation made on the Ethereum blockchain. Gas is purchased for Ether from the miners that execute the code at the time of execution. So the miners actually set the gas cost, who's ever setting the transaction sets the gas cost, and the miners mine depending on what's the most valuable thing for them to mine from the pool. So there's contracts, and the contracts are simply a collection of code, which are functions and data state. So pretty much contracts are like objects. They're just state and functionality. They reside in a specific address on the Ethereum blockchain like we talked about. And contracts are written in a high-level language, which is then compiled to EVM bytecode and then uploaded or deployed to the blockchain. So I'm actually going to, because you guys asked for some you wanted to see me run stuff in the browser. I'm gonna compile something down to EVM bytecode for you guys, a token contract, and deploy that onto a private Ethereum blockchain. So the high-level language that we're using that's going to compile down to EVM bytecode here is Solidity. That's the language of the Ethereum blockchain, the most de facto language. They tried to make one called Serpent, which was Python-looking language, but this was the one that really took off. So it's statically typed, like C++.
Is JavaScript-like? That might have helped.
Yeah, it's JavaScript-like. It's statically typed. It's JavaScript-like, C++, Python, all kind of meshed into one. Statically typed, it's compiled by a Solidity compiler, and they call it contract-based instead of object-based. Contracts are essentially our objects, and they're going to be interacting with each other, and they're going to have, if you're running testing on it, your integration testing is going to be between the contracts, as if they were objects. So we're going to start just talking about the value types in Solidity. Very simple stuff. If you're familiar with coding at all, there's Booleans, true or false values. For this example, it's just you can just type in bool paused, and that's the same thing as bool paused equals false. They're default values. Java does that as well, I'm pretty sure. Integers, there's unsigned integers, uints, and then there's signed integers, and they go from int 8 to int 256 in steps of 8. So you could have int 16, 32, and that's how many bits there are in it. There's also fixed size bytes arrays, which hold a sequence of bytes from bytes 1 to bytes 32. So it's the same size as integers. Bytes 32 is the same size as int 256. But they are meant to hold different types of data. So I put this here, this bytes 32 block hash is block hash block number. So I just wanted to go over some of these units and globally available variables. So you have the block hash, the current block miner's address, the current block difficulty, the block gas limit, the block number. So sometimes we'll use the block hash or the block number to mock random number generation. We're going to use that to randomly generate numbers. Another important thing are these MSGs, the message, the message.gas, or no, the message.sender is who sent the message. So that's going to be whoever called the function. So if a contract is calling a function in another contract, then the sender is that contract. So it's not always the transaction.origin is where the sender of the transaction comes from, which is always going to be an externally owned account. There's addresses are Solidity.
So when you send when you send a request to a contract, and that contract calls another contract, in that second contract, you will be exposed. Your address will be exposed.
Yes.
All the way down the chain.
Yeah, you can always find it. It gets passed along, and that's like, it's just called message.sender, so you'll be able to see the last person who sent you the message.
So there's no way to hand off a transaction to another owner?
No. Addresses are a Solidity specific like type, and they just hold a 20 byte value that's meant to represent an account on the Ethereum network. So like this would be the wallet address. This is the wallet address for the DOA actually. So if you want to send money to them, you can just, you know.
Oh, what's your address, please?
Yeah.
Yeah. Hey.
I should have put my address there.
What's DOA?
The DOA was, do you know what that was? It was a big deal in the Ethereum space. Do you know what it was, Mark?
No, it was the DAO. So
The
they
DAO.
thought that
DAO.
they were making a venture fund, and then there was a bug in the contract, so
That's what.
it was a big fun.
Mm-hmm.
That's when they discovered was that the recursive, yeah, I think that was the origin of the recursive bug.
Okay. And then there's also just enums, like in most other languages. So this would be like subscription terminator, and the two values are provider and subscriber.
Did you say DOA or DAO?
It's DAO is what it is.
Yeah,
It's the
okay, that's
DAO.
why I heard you say
I thought it was
DAO.
in the artificial culture or
Yeah.
something.
Yeah. Yeah, I used to do the same thing.
So all these value types are passed by value.
Distributed, right? Autonomous organization.
Okay. All these value types, they're called value types because they're passed by value. Every time they're moved, they're not copied. It's not like pointers. They're not pointers because these are the pointers, the reference types. They have arrays, which are containers for one type of element, like I'm sure you're familiar with, and then structs, which are containers for related variables. It's kind of interesting how they do like how they show this. Like a 5x4 array is 4, 5, so it goes backwards. There's no multi-variable arrays in any of the code that I'm going to show you though, so just something to point out. And then the structs, you see here we have like a UN64 9696. The reason that we did this, you can pack your variables to make it so they come out to 256 bits because a word in Solidity is 256 bits. So if you do this, you're going to save gaps, and that's very important. So you actually save a pretty substantial amount of gaps by packing your variables in structs.
That's a good point, because what that means is that good programmers who have good value to the company are those who can write code that in this world is the most compact, efficient code, because you can actually tie cost to what that programmer produces, right? So if you have a programmer that writes really large, verbose code, it gets the job done, but it costs, let's just say it costs $100, right, every time it runs, right? Compared to this other programmer, who he might spend longer, it might cost you double the time because he's good, but his code is like this, and it costs you $10 or something. That's something to be aware of in the future, because it will be a real reality. Whereas today, there's really no measurement or metric as to what value the programmer has in that regard.
There's no MVP, so.
But the point is here, right, is the cost, right? So that really adds a different perspective to writing the code, right?
Mm-hmm. Yeah. Let's see next. Data location. This is also something I've only seen in Solidity. There's actually a third data location I didn't put here. It's called call data, and it's only for parameters. There's memory and there's storage, so you'll actually put like, when you're declaring a variable, you're going to put the name, you're going to put something like, let me see.
I thought there was a third local, which is just a stat.
It's called call data. So you're gonna put like uint storage and then the name of like dogs or whatever. Or you're gonna do uint memory dogs because you're gonna be inside of a function. You're gonna be inside of a function, and when you're declaring your variables, you need to know, you actually can't declare a uint as that, but you could declare like an array of integers as memory. So this is only going to be alive while I'm running the function, this data. But if I put it in storage, then it's going to store, I'm going to also have to have something out here like an array over here, and they're going to have to, you would put like, I would reference, this would be a reference to that, I think. I'm trying to remember, sorry. But those are the two main types, are the storage and the memory. So the memory is temporary, like I was trying to explain, and that's only function calls they stay alive for. And the storage is permanent. It gets stored in the blockchain if you're doing
Something to point out here regarding that memory, this hurts a lot of people. It's stack driven, all right? And that stack is finite. And when you start chaining contracts together, or you write certain kind of code that's recursive, you're going to eat stack up. Okay? You need to be smart and manage that stack and understand what effect you have on the stack, because if you call another contract and it starts executing and runs out of stack, your stack, by the way, because the call contract inherits everything your context, your runtime. Okay? So everything you have running is exposed to who you call. So if you're calling a trusted third, you think it's a trusted third-party contract with a partner, but just went rogue on you, okay. But if you're calling a contract that you wrote to, a lot of difference. Okay. The point is manage the stack, because if you call and you end up down the chain running out of that stack, well, guess what? It doesn't complete, and everything's going to roll back in your hose.
And you spent your gas.
Yeah, your gas is gone.
Yeah, and the gas is a big thing here. It's really expensive to store something on the Ethereum blockchain as opposed to just running something in memory. To do like a load into memory is only 3 gas. To store it is is 3, and to do a load for storage is 50. So and that's just like to pull data is 50. To add or modify data is 200. So it's,
think of those as dollars.
Yeah.
To get the scale in perspective. So what does that mean? That means you want to write and you want to design systems that minimize what you store on that chain. So if you think you're going to put your Oracle customer service database that's 2 petabytes on Ethereum, think again.
Is any of this, or is any of this like taken into consideration with the POS, the voluntary option?
I'm sorry?
Like, isn't Ethereum switching over to proof of stake?
Yeah, but proof of stake, it's the same thing. It doesn't
So this
matter. But the proof of stake is just a replacement for the proof of work right now, because it costs too much and it eats up too much. So the proof of stake is just a game where you have skin in the game. But basically what it is, it's a franchise model, right? Whoever wants to, I think that initially what I heard was like 40 nodes. Okay, 40 nodes should be able to handle the world for them starting out of the gate. So it's like, think about the stock market has seats, right? And you want to trade stock, you want to be a market maker. That's what the nodes are, right? They're market makers, I mean, in a way, right? So they're there making the market, right? So they auction off the seats and they pay. So I don't know what it costs for a New York seat, but you know, in the early days you could have got one for like 50 grand. Today it costs you maybe 5 million or more, right? So getting a node, one of those 40 nodes, think about it. If you're one of those 40 nodes, you're going to be the Google of tomorrow, right? And as long as you can keep the whole idea is that if all of those nodes are independent entities with stake in it, So if they want to screw us, they're going to lose their stake, and losing their stake outweighs, right? It's just a game theory, right? Don't want to, if it pay to be a bad guy, because if it does, I'm going to be a bad guy, right? But if it pays to be good, I'll be good. Or, you know, if there's an incentive for me, I'm a bad guy, but I don't see an opening, I'm going to sit and wait. It might be eternity, but I'm going to sit and wait, and if I get the opportunity, I'm going to jump on it and rob you blind. So I'm a bad guy. That's life. That's what we're dealing with here. That's why we're going to have custodians. From the banks are going to turn into custodians of your keys and other trusted things, like your crypto or whatever, your tokenized assets. They hold your money today, but tomorrow they'll hold your DNA.
I just was wondering if that was ever brought up.
And you'll pay them, too, to protect them for you.
You're asking now if the cost has been considered.
Right.
Will it very well? I mean, it certainly probably will,
Yeah.
but it's still going to be a cost.
Yeah, and I don't even know where they're at in terms of implementing that.
Well, it might not even happen. So, what we call, there's a hierarchy that's happening. I hope I get to show the slides.
Okay,
at the
sorry,
end,
didn't mean to.
The way things are breaking out.
Okay, let's see. All right, this other type, mapping types, they're like Python dictionaries, just key value stores.
Associative arrays.
Yeah, associative arrays, exactly. So you have, here there's a mapping of an address to unsigned integer, it's just called balances. So you have all these addresses and they all point to a number and that's the balances.
If you're a Java programmer, think of a map.
So here's a first example. It's just a pretty simple crowdfunding example. There's two structs. There's the funder, which is just an address and an amount, and then there's the campaign, which is a beneficiary, a funding goal, number of funders, amount, and funders, which is a mapping of integer to funder, which is just going to be like the funder ID, pretty much. So this is, I guess I should explain at the top, there's a pragma solidity. This means the compiler version. So this is compiler versions greater than 0.4.11 and 0.60 is what this is going to run with. So then you define a contract, and then inside is pretty much what we reviewed, like a couple structs, and then the number of campaigns, and then another mapping of you into campaign. So it's going to be like a campaign ID in the campaign itself, which is here. So then you're going to be able to create a new campaign, and anyone can call these functions because they're public. We're going to talk about function visibility in a little bit, but all of these are public functions, so that means anybody can call these functions. You have to remember that, it's super important. And then functions also have this cool thing, returns. So this is the returns parameter. So it's going to return a campaign ID that's a uint. So that's why you actually don't even see a return call down here, because it already knows that it's going to return campaign ID. So here, this is also declaring it. So you're declaring campaign ID in the function declaration. Campaign ID equals the number of campaigns plus plus. So that runs, and the next the campaign ID equals the campaign with the beneficiary that goes here and the goal, and then with 0 funders and 0 amount, because it's just creating a campaign here. And then when the function ends, it returns this value, the campaign ID.
So that's storage.
Yes, this is storage. Yes, this is storage.
So every entry you put in there has a cost.
Yep, 200 gas. So,
So the storage is the number of, is it by transaction, by bytecode, or by bytes stored?
it's
By
by
bytecode, right?
each time you call it, the opcode gets called. Is that what you're asking?
Yeah, and then you get the meter. So what I'm saying is, so the meter's 200, so what's the difference between me storing 1 byte and me storing 1 million bytes?
Well, 1 byte is gonna be like bytes 1. It depends on, I mean, it costs.
1 call.
Yeah, 1 call costs the same to do like a UINT 256. That's why you're best with packing your structs, because it's 1 word at a
It's
time.
gonna repart my 1 megabyte in the call, so I can't pack the call. That's what you're saying is, you can't.
The most bytes you can store together is 32.
What I'm looking at, no, because what you're storing is the struct,
Uh-huh.
right? I can pack 1 million bytes inside the struct,
Yeah.
and I can now create the struct and store it as 1 call and that's 200. So what I'm saying is whether I put 1 in there or 1 million in there and I make the call, right? Am I just going to see a charge of 200?
No, because these are UINTs. These ones that say UINT, those are UINT 256. It just isn't written all the way out. So each one of those is going to be a full call, because the size of a
So
word.
the granularity goes down to those of
Yeah.
the cost.
Mm-hmm.
Okay.
I think the size of an address is 256. It's 20 bytes, actually, is what that is. But it says payable here, too. That means this...
So what we're saying here is that for you guys that are advanced or thinking out, there definitely will be a market and someone can make probably hundreds of millions of dollars or more, whoever has the de facto linter, right? Think about it, what we're talking about. An advanced linter, I'm talking about a syntax linter. That's easy, that's kindergarten. I'm talking about an advanced linter that goes out and can simulate and understand the cost of that contract, right? And then, because it's big data and it's looked at 10 million of those, it'll be able to tell you for a nice fee through AI how you might want to restructure and give you a few options. Because when you look at this code, I know I look at it all day long, it's pattern driven. It's a pattern everywhere. The code right now is very concise. It's not like other languages that have lived for a long time and gone through many iterations, right? It starts out with 10 instructions, like Java started out with 1,000 method calls. Today it's got 150,000 method calls, and I'm supposed to know every one of them to pass an interview test. Okay? That's great, right? Crazy. So the same thing will happen here probably too as it builds out. Hopefully we'll see where it goes, but keep that in mind.
So, this is when you're going to see someone using the storage keyword. Here in the contribute function, you're saying that this variable C is the storage from the campaign's campaign ID. So it pulls it in, it does storage, because then we can start making calls to that variable and store it in our storage. And then here you're seeing the amount that gets stored is the message.value, which is the ether that was sent along with the call. So there's actually a decent amount of work that has to go into behind the scenes actually calling a call, which is why MetaMask is really helpful, because you don't have to do anything really with that. Check goal reach.
That's a big disconnect right now in the world if you're developing dApps. There's a big disconnect when you go to the user experience level, because you got a beautiful dApp, but how do you get the transaction signed, right? Because the world of keys lives outside you, and your user has to be able to present and sign a transaction that you want to run. How did that happen? Well, right now it's a big disconnect. People roll their own solutions, but right, it needs to be universal. That's where WhatsApp can come in.
And then down here in the check goal reached, it's some basic code, but the one thing I want to point out is where it says c.beneficiary.transfer. This .transfer method is built into the payable addresses. So we're going to transfer the amount from this contract to that beneficiary if the goal is reached. And this is a good time to point out a re-entrancy attack too, or a preventing one. What we do is we check the amount that it's less than the funding goal, and if it is, we just return false and we end the function call. But otherwise, if we have reached the funding goal amount, then we're going to say, we're going to create a new variable called amount, and we're going to set it equal to C dot amount. Then we're going to change the storage to equal to 0. So like the storage gets set to 0, and then we send the money to the beneficiary. So a reentrancy attack calls this again and again and again and again, and if you don't set the storage to 0, then you could be draining the contract.
It's also a pattern you want to look at just in general, because when you call out, it could never end. And if you've already set state, that state, or you're expecting state to come back or change, and it doesn't, guess what? You end up with an account, you have to end up with a transaction halfway finished. So somebody might have got debited, but somebody didn't get credited, or vice versa.
Right, can you explain that again a little dense? Why do you assign the amount to 0?
Oh, well, it's called checks effects interaction, but you want to assign the C dot amount is C is in the storage, so that's actually stored on the blockchain, and it's set to like 300, right? And then if we didn't have that, and it's C dot beneficiary dot transfer C dot amount, then it's just gonna, and then you put C dot amount equals 0 after that, then if you could have a function that calls this contract and calls check goal reached a bunch of times.
I see.
Okay.
Okay.
And then eventually the C dot amount is never gonna go through, and you're just gonna.
I got a question. So you have some, you're not obviously defining the memory and the storage except for in the one spot. So these are defaulting to memory unless you define it as storage except for.
Memory function parameters default to memory, and storage default to local variables. So, and they're forced for state variables.
Right, the state variables is basically a state machine.
Yeah, that's how the stack is building up.
Yeah.
That's why you gotta be careful, because you might get something coming in on a call, and then you're going out bringing in something, right? Your stack starts here, you end up here, you make a call out, and they wanna add to it, and you blow the stack, and the transaction blows up on you. And that's what would happen if I didn't set the amount right. I already set the amount, transaction finished, right? So, whereas he's talking about in the end, it's like I'm supposed to set the state coming back, state never comes back, so I never update you. I sent your money, and that's reentrancy. Just keep, right? The contract thinks you always got 200. That's crazy.
Okay, error handling, there's 3 ways to handle.
Oh, another point too. People right now are engineering contracts that masquerade, right? So it's like, because when contracts interact, right, they open up holes. So it's like there's like a redirection attack that's happening where you can call a contract, get redirected, and then they switch out and they think they're calling you, but the address they're calling is a contract that you created, who they think is you, which is an owner, but because it's a contract, a different set of semantics takes place. So depending upon the call, if it's the right kind of call, you can then go right back into their context and then empty their wallet, empty any, literally whatever storage they have, as far as Ether, if they're storing whatever you can dump it.
So there's 3 ways to error handle, and all 3 of these methods that are built in undo all state changes. But when an assert statement fails, what happens is all of the gas gets used up that was sent. So when an assert statement fails, something very wrong and unexpected has happened, and you just want to eat up all the gas, just in case there was a reason that something very wrong happened, and the caller was malicious. So you don't want to leave any gas around for anything to happen. The only time we really see this going forward is like require statements. So function visibility, there's 4 types of functions. We saw the public ones, which are callable internally as well as externally. External are only callable by other contracts and via transactions. Internal are callable internally and are also visible to contracts derived from this contract. And then private are only visible by the contract in which this function is defined.
You say derived. Contracts derived from this contract.
Yeah, so
This contract.
inheritance.
Yeah, okay. It's inheritance.
Yeah. So function modifiers, these are pretty cool. This is a simple example of a function modifier. You use the modifier keyword, you name it, and then you write some code, require message.sender to be owner, and this is the error message that returns on the require, and then you put underscore semicolon, and that means run the rest of my code. So you do, so this contract mortal is owned is called, has the only owner modifier on it, so self-destruct gets called, which is an internal method which just destroys all the contract code. The only way for that to get called is if the message.sender is the owner. So it has to pass through the modifier statement first. Modifiers are really useful in Solidity. Special function types, these aren't too big of a deal, but I mean, I guess they are. There's view and there's pure. View functions promise to not modify the state of the contract, and pure functions promise not to read from or modify the state. And since the state of the blockchain is not modified, network verification is unnecessary, and these function calls are free. They're transactionless when called via Web3 or any other RPC wrapper API. RPC is remote procedure call, which is just the underlying code that calls the Ethereum blockchain.
So if you create a chain analysis tool, it's all for free, baby, right now. Because you can read that as much as you want, and then compile and turn that into analytics and sell it. Hello, chain analysis.
But it's mostly used at every point. Besides that, is if you want to just see what the state of the contract is.
Well, right now, for chain analysis, they said last year 90% of their business, they just got up to 200 million now in funding, right? Or something, or revenue or something, whatever, but I just read it. But the point was, the article came out and said that last year, it was, I think 80%, 80 or 90, very high, was law enforcement, okay? But now their model has shifted this year. 40% is enterprise. What financial? What? Know your customer. Because as we enter into a crypto world, right, it becomes very important to know your customer. And how do you use crypto customers? How do you understand them? It's not like mom and pop coming in, know your customer, right? Or some businessman, give you the papers, right? Make some phone calls, whatever, fact, whatever. So chain analysis has very, obviously now created these very sophisticated algorithms, graph algorithms that crawl the chain and build these metrics that can show, right, the probabilities. I'm just surmising, right? Obviously, a correlation. Not going to be alone, but in a correlated manner, because everything is a graph, right, on the chain, and you can follow. But it's huge. I think it's the blockchain now with Ethereum is like what, 400 meg, or I mean 400 gig now, 400 gig.
Potentially, I don't know.
Yeah. So it's like, I mean, the number of right. So that's big data, and then making sense out of it. Well, they figured they've got a magic formula for it, right? So, and obviously it was very important to law enforcement. And Silk Road, I mean, that's how they got nabbed. I mean, you gotta be really a good criminal to get on these chains if you don't understand that, you leave trails. Oh, point two, Monero and Zcash, they did come out and say that they did admit that those two, they don't really get a whole lot out of them. Okay, so those two are called black boxes. Right, zero knowledge proofs that are implemented in cryptocurrency. So the whole idea there is to obfuscate the parties having the transactions. Okay, that's their whole sole purpose, is to create dark transactions. Utilizing the public internet, or the public blockchain.
Creating contracts is something we can do with our code, just with this new keyword. We have a contract here, and we have a function in this other contract, the bakery, that you just call new cookie. It just calls it. It just creates a new cookie. So it actually goes onto the chain and deploys that contract for you. And then when you do contracts.push this, it's going to push an address, the address of the newly created contract to this array, so you can know where all your contracts are stored. Events, we're talking about pulling data from the blockchain. This is how you do it. Each transaction has an attached receipt which contains 0 or more log entries. These log entries represent the result of events having fired from a smart contract, and the indexed keyword will allow you to search for events using the indexed parameters as filters. So for this one, you have an event. It's called data subscription end. So you have the provider of the data, the subscriber of the data, and the terminator who terminated the contract or the subscription. We're going to look at this shortly. Inheritance exists in Solidity also, like it's contract oriented, contracts are the objects. This mortal contract is owned, so that means that we can, we have to, when the owned has a constructor on it, so when mortal is created, the constructor gets called, the owner gets set to message.sender, and then the mortal contract has a kill function, which if message.sender is the owner, then self-destruct. It's pretty much what we saw earlier with the modifier, if message sender equals owner. That's a big thing you'll see a lot, because we want to know who the message.sender is to, you know, authenticate for function.
It's like extends in Java and requires in, or import in JavaScript.
Mm-hmm. So now we're going to talk about ERC20 tokens. They're Ethereum-specific cryptocurrency that are being used as the unit of exchange in dApps or as stock in a company. They're typically purchased with Ether, and this is the standard that tokens need to follow to be listed on an exchange, like as to this point. Some exchanges also do ERC 721 tokens, I think, non-fungible, which we're also going to talk about. But this is the code for token. But what we're going to do is we're going to go to Open Zeppelin contracts. Open Zeppelin is a big library for Solidity. So
In many ways, you guys can look at these as like interfaces.
What is it called?
Open Zeppelin.
Yeah, Open Zeppelin is a company you want to know because they already have contracts, and their business model, well, right now, I mean, where they're trying to evolve to is they want to be that library layer that you go to and inherit from to start building your contracts. So all the heavy lifting they'll do, and they started out essentially as auditors, security auditors, right? And then they just built. They've seen so much code, right? And they've discovered so much. They built their own library. They have best of breed contracts. It's all on GitHub. It's all available for you to clone and do what you want with. And they're already also on net too, so that you can literally include them and you don't have to actually build them in. But that's scary, right? Third-party libraries.
All right, so this is ERC20. This is the tokens. Anytime you hear about tokens, they're mostly ERC20. They're at least going to be ERC20 compliant. Sometimes they'll do stuff that extends the functionality, but this is the basic functionality of an ERC20 token. I'm just dropping this interface that they have. This other thing that they're using here, it's called Safe Math. So they go using Safe Math. That's a library. Using Safe Math for uint 256 means that when I have a uint 256, I can call methods from the Safe Math library on it. Like, let's see. Okay, like balances 2 returns is a U integer. It's the balances of someone. It's an integer, and I can call .add on it, which is Safe Math. So I guess we'll download Safe Math also.
You want to use them too for just general things like multiplication. Something as stupid, simple as multiplication can really kill you in that smart contract if you don't do it right. You don't understand what you're multiplying.
I'm trying to think where it is in here.
It's not always as simple as multiplying integers.
Oh, thank you.
Yeah.
they just made these. Let me see what it's called in this other one first. Yeah, that's what it's called.
Yeah, that's super common contracts.
Also, for you guys that are just starting out, truffle, TRUFFLE is a great way to get started.
Yeah, truffle. We're gonna use truffle actually, I think.
Cool.
At least to compile contracts. So import safemath.sol. So we're gonna just break this down to what we actually need. So you got your total supply, which is a private integer. So this is how we create. Is there a constructor on this? Guess not. Well, anyways, they have a total supply. Because this one, they're making it so you can burn and mint tokens. They're making it so they can mint tokens infinitely and burn tokens upon request. But you could get rid of that and just have a total supply of something like whatever you want. That's what I put in here. I guess we can look at this and then go back to the other one. Here we have the balances is just an address to an unsigned integer. So those are all the balances. The allowed is an address. It's a mapping to a mapping. So you have your address, which is the owner, and it points to people that can spend, and that points to how much those people can spend. So that's how many people are allowed. It's called the allowed. And then you have a total supply, 1,000,000 tokens, balance of. Then you just have these. This returns the total supply. This returns the balance of an owner at any address. And then this is what matters, the transfer. There's a transfer method, which this is really the coolest thing about it is when you transfer tokens from someone, all that happens is that this method is being called within this token contract, and it subtracts the balance of the person that the money is from, and it adds that to the balance of the person that money is going to. All it does is subtract and add, and that's it.
Well, that's a little bit of Bitcoin in there.
Yeah.
That's all that Bitcoin does.
And then there's also a transfer from where I can transfer money from one account to another account. So I'm going to want to approve, say I'm using an application, a decentralized application, and I want to approve someone to transfer money for me. Like say there's someone that uses the application that's really good at the application, whether it be a game or investing or whatever it be. I have all of my money tied up here, but I want this investor to be able to use my money. So I'm going to say, I'm going to call approve, and then it's going to approve that my money can be sent by this person up to whatever value I approve them for. So you can approve a person or an application or like a contract at a certain address to do that.
One quick question. Why we are assigning the total supply like a big number?
We are just setting a total supply.
It's like a common use case.
We just created the.
In the real world, that number will be determined by your economic model.
Yeah, that's what because I can't define myself as like have 10 million tokens.
Well, if you're going to make your own token, then you're going to define what your economic model is, right? And then you'll figure
You
out
can do it if you
how
want.
much you need.
Yeah,
You can do it if you want, it doesn't mean they're worth anything, you just made a whole bunch of tokens.
And you don't have to have
Yeah,
a
I mean,
fixed supply
it could
either.
be 3, or it could be 3 billion.
Yeah, what do they do?
Yeah, you don't need to have a fixed supply. Like in this ERC20 token, it has a mint. This function that calls mint, and then when it gets called, you see the total supply gets added to the value, however much you're minting, and then it's getting sent to the account that you're minting to. And you just can't mint to the 0 account. because they just set that as a requirement. But
Yeah, I mean, it's no different than the Federal Reserve printing money. You know, just get the paper sheets, put the ink, and start rolling it through. Stop when you want. That's what that is too.
and I guess we could try to start.
And that burn function came through evolving of the ICO and the token model because they realized that there was economic efficiencies to be able to burn tokens, just like the feds take money out of circulation to keep the supply where they believe it should be in order to keep inflation under control.
Actually, that is the deflation. by
Yeah,
definition.
yeah, exactly, yeah. So, I mean, and if you're making those tokens, that's part of your problem, because you have to be the central bank now. You have to maintain stability and value, because if everybody's selling your token, obviously the price is gonna start plummeting, so you have to have reserves and start buying them, you know, to even it out. That's the market maker, right? Well, in an unregulated world we are today, smart operators are using this, they have been using this mechanism to make billions of dollars for free.
Okay, so this genesis.json file, I'm kind of going on a little tangent here. I think you guys will like this. This is all that's needed to create an Ethereum blockchain. It's Genesis file. You have your chain ID, which can be any integer number. You probably, if you're trying to make it a private chain, you probably want something a little longer than this and very randomized, and then no one's really going to be able to find your chain. Then this is like the Homestead block. These are set to 0. Homestead was a version of Solidity. And then, so
Chain ID is always numeric, or can it be?
chain ID has to be numeric.
Okay.
Yeah. I'm not versed in all of this here. There's like the gas limit.
The reason because the chains, the real chains, are identified by their numbers.
Okay.
So like, I think Rinkeby, which is a test chain, I think it's what, 4, right? And then of course the main chain is 1, right? So, and the thing is that you can, and there will be others, and it's actually a business model today, right? To create a test chain, okay? And because whether, right now, those test chains are wide open. There's no regular, I mean, they're like abused. You can be abused easily. It's all fake money, but the point is that when you go on there, like me, a developer, you actually try to want to get work done, there's people out there messing with you. Because they make everybody know, everybody's on the chain, everybody can see everything, right? Within a certain radius. But the point is that there's no quality of service, no quality of control, right? So there is a market for someone who can create a test chain, create a franchise model, right? Enlist people, build the trust, be the HR, right? And for a small fee, like Netflix, $9 a month, right? You can join on the chain and you can develop on that chain, and we actually provide service for you to help you. Okay? Once people figure that out, and somebody does it, then there'll be a lot more, because it'll be evolutionary and we'll figure out what's the best way to get into that market, because who's your customer? Right? Again, it's probably premature now, right? But now's the time to do it. Just like custodians, keeping keys. Okay? Y'all heard of Vault, company Vault, here in town? No? It's a Vault company? A wallet? Yeah, it's a wallet company, and they're getting real hot, because they figured out that instead of trying to be, quote, a wallet, being the wallet, just like everybody wanted to be chain, they figured out that there's more money to be made by being an API. And providing all of our work we did to create our wallet that nobody really wants, it's too hard to sell, too competitive, but all that infrastructure we created, it's only like 5 megabytes, and we can put any facade on it we want, so we're going to sell that. And what they're doing as an SDK to anybody who wants to get to the market quick.
Abra?
Huh?
Are you talking about Abra?
Company called Vault here in town.
Vault.
Vault, V-A-U-L-T, Vault Wallet, here in town, they're trying to raise money now. V, as in Victor,
A-U-L-T?
yeah, like the vault, like a money vault.
Like a safe?
So they also.
So they'll do like, and they're here, and they're already in operation, and they're trying to go to the next stage. So they have some investors, and they'll do a white label, right? So you can do an app, but the back end is them, so you don't have to deal with all the white. So they'll hook you, basically they take your either legacy application or your new application, and then they'll put the blockchain, wire up the blockchain to it with that very API layer, so that you can just deal with your business domain and pass off to them their API, and their API will do all that heavy lifting to the blockchain for you. Well, that's a huge market. So and they're going after the enterprise because they see within the enterprise companies were going to be wanting to put their product, certain product, right, or applications in crypto and on the blockchain, because once you play it out, the model, it's like crack. Once you do it, you don't want to go back. You don't want anything else. It's like you're addicted. You can't get it out of your head. You can't figure out a better way. Right? So it's like, you know what I mean? It's like once you get a bicycle, you start riding a bicycle, why do you want to walk 5 miles? Right? And then you get a car, why do you want to ride a bike? This is what this is.
And I notice you're not using Remix.
No, I'm just using Truffle
Yeah.
to compile my contracts.
Is that just a preference?
It's just it's a what's it called framework. It's like a.
Oh, I know what Truffle is.
Oh,
I'm
okay.
asking why you choose
I
it.
just thought that it always made my development faster to use Truffle.
Yeah, well, actually, once you get into production mode, you'll roll your own workflow, because at the end of the day, it's just text and compile, right? And then the key is that you realize that you're going to need Ganache, right? You want Ganache,
Which is your
right?
local.
Because the new Ganache, right? Because that gives you a local test blockchain with addresses and all that, right? You typically start out of the gate, you'll have MetaMask, so you can do the signing.
I
and get the
asked
prompts.
him about Remix.
Yeah, I use Remix. Remix is great for proofing, validating a contract, right? Cut and paste, it'll compile and validate for you. It's good for getting the API. It's good for quick, dirty prototyping, right? But I'm talking about when you're in full mode production, right? Then I don't know about